Okay, so in this next section of Chapter 3, we're going to kind of go back to compounds and how stoichiometry and these stoichiometric relationships kind of play out in our overall chemical formulas for compounds, as well as just determining what's actually in a compound, okay? And so the first thing that we introduce when we're talking about this composition of compounds is something called the mass percent composition, or the mass percent, all right? And so this is defined as the mass or percentage of the total mass of the compound that an element makes up, okay? And so we define that as the mass of element in 1 mole of compound divided by the mass of 1 mole of the compound. So what does that really mean in actual chemical terms? All right, so for example, let's say that we wanted to know what the mass percent composition of chlorine in a compound like this CCl2F2. So if we drew out the structural formula for this, for the CCl2F2, we would find that we have carbon bound to 2 chlorines and 2 fluorines, okay? And so if we're wanting to know what the mass percent of chlorine is, what we need to know is how much mass of chlorine, or how much mass chlorine provides to this overall compound, and compare that to the total mass of the compound. Okay, so to do that, what we're going to do, again, in determining the mass percent of chlorine in this compound, is we're going to determine, number 1, the overall molar mass of the compound. Okay, so to do that, we're just going to sum up the atomic masses of all of the elements in the compound. So for example, we have 1 carbon. So carbon has a molar mass of 12 grams per mole. We have 2 chlorines, right? So this is 2 times the atomic mass of the 2 chlorines. So this is 2 times 35.45 grams per mole. And then we also have 2 fluorines that we have to account for, and that's 2 times 19 grams per mole. Okay, so when we multiply these guys out and we add all of them together, we end up with a total mass here of 120.91 grams per mole. And again, this is the molar mass of this compound, CCl2F2. Okay, so that is the mass that 1 mole of this compound essentially has. Okay, now for determining this mass percent, we also need to know, well, how much mass is there from chlorine specifically in 1 mole of this compound. So to do that, all we're going to do is multiply the numbers of chlorine in the compound, which is 2, by just the molar mass of chlorine. So we do that. So that's the mass that comes from chlorine. We're going to divide that by the total mass, the total molar mass of the compound, which we just calculated. And then because it's a percent, this is going to end by multiplying by 100. Okay, so the mass percent of chlorine in this compound ends up being 58.64% chlorine by mass. Okay, so how do you determine the mass percent for an element in a compound? You multiply however many of those things are in the compound by the molar mass of the element, and then you divide that by the molar mass of the overall compound, multiply by 100. That will give you the mass percent of an element in a specific compound. So now, how are we going to utilize these mass percents? Because it's like, well, we can do that, great, but what is that going to tell us? So we're going to be able to utilize these mass percent compositions as like a conversion factor, as a means of converting from one thing to another, okay? So just as a note, percent means per 100, right? So percent is per 100. And if we have something that is 58.64% chlorine, that means that for every 100 grams of our overall compound, there are 58.64 grams of chlorine in it. Okay, so that's what the percent means. Anytime you have percent things, you should always assume that you have 100 of that thing. So if we had 100 grams of our compound, then because it's 58% chlorine by mass, there would be 58.64 grams of chlorine. Okay, we're going to be able to utilize this as a conversion factor in different types of problems. Okay, so how exactly would we utilize that? So let's say that we did have a specific mass of this compound. Let's say we had 789 grams of this overall compound. And we wanted to know, well then, how many grams of chlorine are there in this 789 grams? So we're going to be able to utilize our mass percent composition and know that for every 100 grams of our compound, there are 58.64 grams of chlorine. Okay, so we have a mass of a compound, and we want to convert to mass of the element in that overall mass. We're just going to utilize this as a conversion factor. Right, so we have the 789. We're going to go ahead and divide by 100 grams of compound and multiply by the 58.64 grams of chlorine. Okay, so how many grams of chlorine are in this 789? Well, when we multiply, when we divide, we find that we get like 463 grams of chlorine. So again, this is one way that we can utilize these mass percent composition type problems. We can use it as conversion and know that for every 100 grams of the compound, there is whatever percentage of that element in there, that many grams of element in there. And we can convert from various masses of the compound to masses of the actual elements that we're interested in by utilizing those conversions. Okay, so now we can take what we just did essentially with respect to the mass percent compositions is we took our chemical formula, right? So we took our Cl2F2, right? And we utilized this data, right? The fact that there is 1 carbon, 2 chlorines, 2 fluorines to figure out the mass percent of an element in that compound, right? So we figured out mass percent chlorine. We could have done that for fluorine and carbon as well, okay? So now the question is, can we do the reverse? Could we take a mass percent and could we figure out what the overall chemical formula was, okay? And so the answer to that is yes, we can, but it's kind of like a qualified yes, because what we end up getting is not necessarily the molecular formula, which is what we would like to get, our molecular formula, but instead we only can determine the empirical formula from it, okay? So again, yes, we can take mass percent composition data and determine a chemical formula, but that chemical formula will only be the empirical formula. So remember, what was the empirical formula? It was the simplest whole number ratio of atoms in a compound, right? So for example, hydrogen peroxide is H2O2. This is the molecular formula. The empirical formula is, again, the reduced number for these guys, the simplest whole number ratio. So the empirical formula for hydrogen peroxide, H2O2, would be just HO, okay? So with respect to taking mass percent composition data and figuring out the chemical formula, we can do that, but all we can determine from that is the empirical formula and not the molecular formula, okay? So we would also have to have other data to figure out the overall molecular formula. So this technique, this essentially utilizing this mass percent composition data, using it to determine the chemical formula, this is something that is called elemental analysis, okay? So what will happen usually is you will take some sort of unknown compound, you will decompose it, and then you will measure the masses of all the elements in it, and then be able to extrapolate back to get the empirical formula. So how would this actually go about working, right? So let's say that we have a sample of water in the lab, okay? So we go in, we don't know the chemical formula of water, but what we do know is that it contains hydrogen and it also contains oxygen, right? And so we don't know what these ratios are between how many hydrogens versus how many oxygens are in this compound. And so we take our little unknown water sample and we decompose it. Okay, so we break it down completely into hydrogen and oxygen, and we measure the mass of both of those elements. Okay, and so what we find is that we end up, when we break this compound down, with 0.87 grams of hydrogen, and we have 6.86 grams of oxygen. Okay, so how would we go about utilizing this data to figure out what the empirical formula is? So just note that when we're dealing with these little guys, our little subscripts, these guys are in terms of actual numbers of molecules, right? This is going to tell us, oh, for every 2 hydrogen, you get 1 oxygen. And if we drew the structural formula for this, you could see that for every 2 hydrogen, there's only 1 oxygen, okay? With respect to this is not dealing with relationships between hydrogen and oxygen in mass. Instead, these again are dealing with hydrogen and oxygen relationships in molecules, okay? Or more importantly, in moles. So the first step in this is going to be taking our masses and having to convert to moles. So that's going to be number 1. So how would we go about doing that? So we're going to go ahead and take the masses that we were given of each of the 2 elements. So we've got the 0.857 grams of hydrogen and 6.8 grams of oxygen. And our first step in doing this is converting these to moles. Okay, so number 1, we're going to convert our grams to moles. Okay, so we'll take our individual masses. We'll start with hydrogen. We've got 0.857 grams of hydrogen. And to convert to moles, I'm going to take the molar mass of hydrogen, which is for hydrogen just the atomic mass, 1.008 grams per mole. And I'm going to go ahead and divide by that, right? So to convert from grams to moles, we're just going to divide by the molar mass. So for every 1.008 grams of hydrogen, we would have 1 mole of hydrogen. So when I do that, I end up with 0.850 moles of hydrogen. And now I'm going to do the exact same thing for oxygen. So for oxygen, I have 6.86 grams. I'm going to take that mass and again convert to moles by dividing by the molar mass of oxygen. So oxygen is 16 grams per mole. So I'm going to take the mass that I have, I'm going to divide by the molar mass to convert to moles. And that's going to leave me with 0.429 moles of oxygen. Okay, so first step is conversion of your masses of the elements to moles. Okay, then what we're going to do is we are going to write what is called the pseudo formula. Okay, so in the pseudo formula, we're going to write the 2 or the multiple, however many elements we're dealing with, in kind of like a putative chemical formula. Okay, so we'll say hydrogen and oxygen. And then what we're going to do is we're going to list as the subscripts how many moles of each we have. So for this one, we've got 0.85, and I may need a little bit more room. So for hydrogen, this is 0.850, and for oxygen, this is 0.429. Okay, so this is what we would call a pseudo formula. Okay, so have you ever seen a chemical formula look something like this? No, you don't usually see it, right? Instead, you see it as nice, even whole number values. So the way we're going to take our pseudo formula and convert it to our actual empirical formula is we're going to divide both of our amounts in moles here by the smallest number of moles. So for this one, the smallest number of moles is from oxygen. There's only 0.429, so I'm going to divide both numbers by that. Pardon me. 0.429, and I am left with H 1.98 and then O reduces down to 1, okay? So when you're left with something like this, which is like within 0.5 of an actual whole number value or 0.5 of a number, then we can go ahead and round up to H2O, which is our trusty, familiar water, okay? All right, so just to kind of restate that action, okay? Again, in a nice little simple chart. So first step in converting all of this mass data to the actual empirical formula is you're going to write down all of the masses of all of the elements that you're dealing with, okay? So there's a note here that if you're dealing with percentages, like mass percents, you should always assume that you start with 100 grams of total mass. You're then going to convert from grams to moles by using the molar mass of each element. You're going to write the pseudo formula using the number of moles that you calculated in 2 as subscripts. And then you're going to divide all of the numbers of moles by the smallest number of moles. And I think I mentioned like 0.5. If the result is within 0.1 of a whole number, round up to the whole number. And then depending on the situation, you may have to multiply all of them by a specific number to get everything in whole numbers. And in this next example, I'm actually going to illustrate when you would need to apply number 5 here. Okay, so we're going to do one more example, and then I have a problem. So we have a compound. It contains both nitrogen and oxygen, and when we take it into the laboratory, we decompose it, we find that we get 24.5 grams of nitrogen and 70 grams of oxygen. So the purpose of this is calculating the empirical formula for this compound. Okay, so again, my first step in this is taking my masses and converting to moles. So I've got 24.5 grams of nitrogen, and I've got 70.0 grams of oxygen. So I look up in the periodic table where nitrogen is. The molar mass of nitrogen is 14.01 grams per mole. And then again, I look up oxygen. The molar mass of oxygen is 16 grams per mole. So I'm going to take my masses, and I'm going to divide by the molar mass for each of the elements. Okay, so I've got nitrogen, 24.5 grams. I'm going to divide by the molar mass. So it's 14.01 grams for every 1 mole. And then same thing for oxygen. I've got 70. I'm going to divide by the molar mass to convert to moles. So for the numbers here, I get 1.75 moles of nitrogen, and I get 4.38 moles of oxygen. All right, so that's step number 1, conversion from our element masses to element moles. Step number 2 is writing the pseudo formula. So we'll write nitrogen first, and we'll list the number of moles with nitrogen. So nitrogen has 1.75 moles, and then oxygen will come second. It has 4.38 moles. And then in the next step, we're going to reduce these to whole number values, ideally by dividing by the smallest number. So for this problem, that ends up being the 1.75 from the nitrogen. So when I do that, I'll get nitrogen 1, so that reduces to 1, and then oxygen is 2.5. Okay, so this is kind of like that last little issue that I had said, the bullet point number 5. Sometimes you will end up in a situation where you still have a fraction for your number, okay? And so you're going to have to multiply by a whole number value. You're going to have to multiply everything to get rid of that fraction, right? So we're left with 2.5. We can't leave this empirical formula like this because you can't have a 0.5 of an oxygen, right? And so we need to multiply this guy by a number to get this 2.5 to a whole number value. So if we multiplied 2.5 by 2, that would take 2.5, multiply that by 2, that takes that up to 5, okay? So depending on the fraction that you're dealing with is going to depend on what you end up having to multiply by here. But when you do, you have to multiply everything by it. So that 2 distributes into the entire compound. So overall, the empirical formula for this would be nitrogen 2 and then oxygen 5. Okay? Okay, so again, masses to moles. Write your pseudo formula, reduce your pseudo formula, and then multiply this out to get fractions out of any type of subscripts that we have. Okay, so now this is the question that I'm going to put on the quiz. This is question 3.8, and we're asking you to do the exact same thing, okay? Except now, number one, big difference is we have 3 separate elements that you're going to have to take masses and convert to moles, right? So you're going to have 3 separate elements in your empirical formula. Number 2, what we're starting with is mass percent compositions, right, for each of the elements. So how are you going to deal with that, right? This isn't a mass like I've been giving you in the 2 examples before. So the big assumption that you should make with respect to these percentages, you should always assume, that you have 100 grams of this compound. So if you do that, and it ends up being 60% by mass carbon, that means that you would have 60 grams of carbon, right? That means that if it's 4.48% hydrogen by mass, then in 100 grams of the compound, there would be 4.48 grams of hydrogen. And then for oxygen, if there was 35% oxygen by mass, then there would be 35.52 grams of oxygen if there were 100 grams of the compound, okay? So with respect to these percent type problems, always assume that you have 100 grams, and then these percentages will just convert directly to the actual mass of each element, okay? So you would start this problem saying that you have 60 grams of carbon, 4.48 grams of hydrogen, and 35.52 grams of oxygen, and then you would go to determine the empirical formula from that data, okay? So I'm going to go ahead, let you guys do this one. This will be on the quiz. Follow the exact same steps as you had in the 2 previous examples, and hopefully you will get the correct answer. Okay, so with all of this empirical formula, elemental analysis stuff, we are only determining the empirical formula from that type of data, right? The issue is that sometimes we would actually like to have the molecular formula. So how do we get the molecular formula from this empirical formula data? So the one key piece of information that we would need if we wanted to determine the molecular formula and we knew the empirical formula is we would also have to know the molar mass of the compound. Okay, so if we have empirical formula, we want molecular formula, we also need to know what the overall molar mass of the compound is to do that. So just remember, or just as a reminder, the molecular formula is just going to be some sort of whole number multiple of the empirical formula, right? So for example, again, if I go back to hydrogen peroxide, H2O2 is the empirical formula multiplied by 2, this whole number multiple, okay? So this guy is always coming from this guy multiplied by some sort of integer value. And so because of that, the molar mass of our overall compound is also some sort of whole number multiple of the empirical formula molar mass. So if we know our empirical formula and we know the molar mass of our compound, we could figure out what that n was, right? What that whole number multiple was. And then with that, determine the molecular formula by multiplying the empirical formula by this whole number multiple, okay? So I will demonstrate what I mean by that on the next slide. So let's say that we had a compound, and again, we've gone in, we've done this elemental analysis procedure, and we have determined that the empirical formula is CH2O. We have also determined that the overall molar mass of the entire compound is 180.2 grams per mole. So we're going to be able to utilize this data to determine what the molecular formula is, okay? So again, if we want to know what that whole number multiple is to get the molecular formula from the empirical formula, we're going to be able to determine that from the molar mass of the compound, which we know, divided by the empirical formula molar mass. Molar mass. Okay, so how would we get the empirical formula molar mass? So the empirical formula for this compound is carbon H2O, right? So how would we get the molar mass for this? Well, we would just add up the individual molar masses for all of the elements in the compound. So for this guy, we've got 1 carbon. So carbon is 12 grams per mole. We've got 2 times hydrogen, which is 2 times 1.008, which gives us 2.06 grams per mole. And then we've got 1 times oxygen, which is 16. So when we sum all of these guys up, we end up with a molar mass for our empirical formula of 30.026 grams per mole. Okay, so again, this is the molar mass of the empirical formula. So now to get in, all we have to do is take the molar mass of the overall compound, which was 180.2, and divide by the empirical formula molar mass, which was 30.026. When we do that, we should get some sort of nice whole number value, and for this problem, that ends up being 6. Okay, so again, that's not the answer to this question. We don't want to know what this whole number multiple is, but instead we want to be able to obtain the molecular formula from that. So now, with this in, we know that the molecular formula is just equal to the empirical formula times this n. Okay, so we've got our CH2O times 6. And so when we multiply this guy in, we get C6H12O6. Okay, so again, purpose of this, if we actually want the overall molecular formula for the compound, we know the empirical formula, we know the molar mass, we'll be able to utilize all of that data to figure out what the molecular formula is. Okay, so then the last part of this section deals with something called combustion analysis. So previously, we used the technique of elemental analysis to determine the empirical formulas for compounds. Combustion analysis is just kind of like a special type of elemental analysis, okay? So this is usually only used for organic compounds, so things that only contain carbon, hydrogen, and oxygen, okay? And so what happens in this technique is that we take our little organic compound, let's say it just has carbon and hydrogen in it. So we'll take this, some sort of unknown amount of carbon, unknown amount of hydrogen. We will combust it, right? So remember, that is just adding it to molecular oxygen. We get some sort of nice big explosion. And the only products from this combustion is CO2 and then also water, okay? So what happens is we take this unknown, we combust it, and we measure the masses of our CO2, the masses of our water as well, and we utilize that data to go back and figure out how much of this was there originally, right? Well, how does that work? So note that with respect to the carbon shows up only in the CO2 that is produced, and for the hydrogen shows up only in the water that is produced, okay? So in this type of analysis, the oxygen is kind of the hard one because it ends up in both compounds, but we can utilize how much of this is there, how much of this is there, to figure out how much of this and how much of this was originally there at the beginning. Okay, so let's go ahead and go through an actual example of a combustion analysis to figure out, again, how we would get the empirical formula from data like this, okay? So in this example, what we're looking at is we've got this unknown compound, and it contains only carbon and hydrogen. So we can go ahead and write some sort of pseudo formula where we have CXHY. We combust it, so we add it to molecular oxygen, and it goes and produces 2.445 grams of CO2. So we get 2.445 0.45 grams of CO2, and then we get 0.6003 grams of water. So we get water and 0.6003 grams of water, right? So how can we utilize this data to figure out what the empirical formula from the original hydrocarbon was? So the first step in this problem is very similar to what we did before, except now we're going to take our masses of our CO2 and water, and we're going to convert to moles of CO2 and water, right? Not moles of element, because now we're actually dealing with these masses of compounds. So for CO2, I will take the mass that I made of it, 2.445 grams of CO2. So the molar mass for CO2 is 2 oxygens, which is 32, plus 1 carbon. This is a C, which is 12. When we add these guys together, it ends up being 44.01 grams per mole. So I'm going to take my mass of CO2 and I'm going to divide by the molar mass of CO2 to convert to moles of CO2. Okay, so this is 44.01 grams of CO2 for every 1 mole. And when I do that, I end up getting a 0.0556 moles of CO2. Okay, I'm going to do the exact same thing now for water. But now for water, we've got 2 times hydrogen, which is 2.016, and then 1 oxygen, which is 16. We add these guys together for the molar mass for water. This is 18.016 grams per mole. So now we're going to take our mass of water that is produced, 0.6003 grams water, and we're going to divide by the molar mass. So this is 18.016 grams for every 1 mole. So when I do that, I end up with 0.0333 moles of H2. All right, so now that we've figured out the moles of our products dependent on the grams, now we're going to be able to utilize that to convert back to actual numbers of moles of carbon, as well as the actual numbers of moles of hydrogen. Okay, so I'm going to take my carbon first because it's nice and easy. At this point in time, we have 0.0556 moles of CO2. And again, with respect to CO2, all of the carbon came from this guy originally, right? And in a CO2 molecule, we have carbon and we have 2 oxygens. So for every 1 overall molecule of this, we end up getting just 1 carbon, right? So that's going to be the exact same conversion when we convert from moles of CO2 to moles of original carbon. So in this CO2 molecule, for every 1 mole or 1 molecule of CO2, there's only 1 mole or 1 molecule of carbon. So we will convert directly from moles of CO2 to moles of carbon, and they will be the exact same number, because again, it's a 1-to-1 relationship. So now we have moles of carbon. Now water, on the other hand, is different. So in water, we have H2O, right? So for every 1 molecule of water, we get 2 molecules of hydrogen when we break everything apart, right? That's going to be the conversion for water. So if we have 0.033 moles of water, for every 1 mole of water, we actually produce 2 moles of hydrogen, because again, there's a 2 in front, or a 2 with respect to the hydrogen, right? So if we decompose all of our little water molecules, we would essentially obtain twice the amount of hydrogen than we actually had in water molecules. So when we convert from moles of water to moles of hydrogen, you always have to multiply by 2 because of the stoichiometry in the water molecule. Okay, so when we do that, we end up with a 0.0666 moles of hydrogen. Okay, so now that we're in our moles of our two elements from our pseudo formula, or from our original empirical formula, we're going to go ahead and write our pseudo formula like we did with respect to the elemental analysis. So now we've got carbon 0.0556, hydrogen 0.0666. We're going to divide by the smallest number. And we are left with carbon, and then hydrogen, and then we actually do this, so 0.66. Hydrogen 1.2, okay? So now this is again going to be one of these awkward fractions. How would we get a 1.2 to a whole number value? What number could we multiply it by? So if we multiplied it by 2, we'd get 2.4. Multiplied by 3, we'd get 3.6, so on and so forth. If we multiplied everything by 5, then 1.2 times 5 gives me 6 overall. So when we do that, we get carbon 5 and then hydrogen 6, because again we're just multiplying 5 in to get rid of that fraction and to get our answer in a nice whole number value, which is how we normally see our beautiful little empirical formulas. Okay, in this last example, we're going to have a similar type of problem. So we have a combustion analysis, we have some sort of unknown hydrocarbon, except now this unknown hydrocarbon has carbon, hydrogen, and oxygen. So in the previous example, we only had carbon and hydrogen, but now we also have oxygen. So I'm going to show you what you need to do when the compound that you're trying to determine the empirical formula for, when it actually has oxygen in it as well, okay? So again, we've taken this thing, and an important thing to note at this point in time for these types of problems is that the compound that we've taken, we have an initial mass of it of 0.8009 grams, okay? So we take 0.8009 grams of this compound, we decompose it, or not decompose it, but we combust it, right? And so that gives us, again, CO2 as well as H2O, and it gives us specifically 1.6004 grams of CO2 and 0.6551 grams of H2O, okay? So now, for this type of problem, there is a slight difference. We're going to go about this the exact same way that we did before, in utilizing the CO2 to tell us how much carbon was there, and utilizing the H2O to tell us how much hydrogen is there, but then we have to do this little twist at the end to figure out how much oxygen is there, okay? So we're going to start the problem the exact same as we did before. I'm going to take my grams of CO2, so I've got 1.6004 grams of CO2, and I'm going to convert that long term to moles of carbon, right? So the first step in that is converting from grams of CO2 to moles of CO2 by using the molar mass of CO2. So the molar mass here is equal to 44.01 grams per mole. So I'm going to take my mass of CO2, I'm going to divide by the molar mass of CO2 for every 1 mole to get my total moles of CO2. So when I do that, I get 0.03636 moles of CO2. So now I'm going to convert to moles of carbon. So this is going to go to moles of carbon, but just using the stoichiometry in the chemical formula, right? So in CO2, for every 1 CO2 that we have, there is 1 carbon in it. So it's a 1-to-1 ratio. So every 1 mole of CO2, we get 1 mole of carbon. That'll convert this to moles of carbon, which is 0.03636 moles of carbon. All right, so that's how we get X here. So now to go about getting Y, which is the moles of hydrogen, we're going to do the same thing, but we're going to start with the mass or the grams of water that was produced in the combustion reaction. So now I'm going to do same thing. I'm going to convert from grams of water, so grams of water, to moles of water by dividing by the molar mass of water. So water is 18.016 grams for every 1 mole. This is of H2O, and that gives me 0.03636 moles of H2O. Okay, so now that I'm in moles of water, I'm going to convert this to moles of hydrogen by using the numerical relationships, the stoichiometry of hydrogen and water, right? So in water, for every 1 water molecule that we have, or every 1 mole of water that we have, there are 2 hydrogen molecules. So for every 1 water, we get 2 hydrogen. For every 1 mole of water, we get 2 moles of hydrogen. So I'm going to take my moles of water, I'm going to multiply by 2.3636 times 2 gives me 0.07272 moles of hydrogen. Okay, so that's the same as before, right? We're taking our grams of our 2 products, we're converting to moles, and we're utilizing those to figure out how many moles of carbon and hydrogen were in the original compound. Now, to get to oxygen, we have to go through this a little bit different process. So right now, the total mass of the compound, which we had measured out originally, so total mass of the compound was 0.8009 grams, okay? And so that is everything together. That is the mass from carbon, the mass from hydrogen, the mass from oxygen. So we could say this is the mass grams from carbon plus the mass grams from hydrogen, and we'll use a different symbol so as not to confuse ourselves. So we'll say X grams of carbon plus Y grams of hydrogen plus Z grams of oxygen, right? All of those added together are going to give us the total mass. So right now, we know how much both carbon and hydrogen essentially contribute to this compound, but we know that amount in moles. So right now, to figure out how much mass is attributable to oxygen, I'm going to go ahead and convert my moles of carbon, my moles of hydrogen, to grams of carbon, grams of hydrogen, by multiplying by the molar mass of the 2 elements, right? So for carbon, for every 1 mole of carbon, there are 12 grams of carbon. So when I do that, I get a mass equal to 0.4367 grams of carbon. And when I do the same thing for hydrogen, for every 1 mole of hydrogen, there's 1.008 grams. I get a 0.07331 grams of hydrogen. So now I can go ahead and plug those in here. So I've got this guy, I've got this guy. I can plug them in to my little equation here and solve for grams that are attributable to oxygen. So this ends up being 0.8009 grams is equal to 0.4367 grams plus 0.07331 grams plus this unknown grams of oxygen. When I solve for this unknown amount of oxygen, oxygen is contributing 0.2909 grams to this overall compound. Okay, so to figure out how much oxygen is there, I have to add up the 2 masses that are coming from carbon and hydrogen and subtract it from the total mass of the compound that was given. So now that I have grams of oxygen, again, long term, we want to know what the empirical formula for this compound is. This X, Y, and Z. Those guys have to be in moles. I do have it in moles for both carbon as well as hydrogen. Now I just have to convert these grams of oxygen to moles of oxygen. I'm going to do that by dividing by the molar mass of oxygen. So this is 16 grams of oxygen for every 1 mole. And that gives me a 0.01818 moles of oxygen. So now I'm going to write my pseudo formula. All right, so I've got carbon, and I'm going to list my moles of carbon here. I've got hydrogen, I'll list my moles of hydrogen, and I've got oxygen, and I will list my moles of oxygen. So this is carbon 0.03636, and I've got hydrogen. This is 0.07272, and then I've got oxygen, and this is 0.01818. So this is the pseudo formula. To go ahead and convert to the empirical formula, I'm going to divide by the smallest number to get these guys hopefully to whole number values. So the smallest number is 0.08 or 0.1818. I'm going to divide everything by that. And we end up here with a nice whole number value for everything. This ends up being carbon 2, hydrogen 4, and oxygen 1. So that is the empirical formula for whatever this compound is that we were trying to determine via combustion analysis. And again, the difference between the one that I just done and this one is what has to happen if you also have an oxygen present in your compound. You have to go back and go through and figure out how much mass is attributable to oxygen and then convert that to moles to get your empirical formula.